In this video, we're going to take a look at some area applications of integration. So in a broader sense, we're going to look at a lot of different applications of integration. And in this particular video, we're going to look at area applications. Basically, we want to find the area between two curves. So the situation is that I have two curves in the plane, and I want to find the area between them. Now, we found signed area using the definite integral. We've done that earlier and probably in a Calc 1 course. So now we want to find the area between two various curves. So for instance, what if I have a parabola and a straight line, and I want to find the area between that parabola and the straight line from x value of 0 to x value of 2. So that's what I've shaded here in green. How could I do that? Now, I want to say this is a more general idea. So here I have a curve in red and a curve in blue. We call it a curve. It's just some function, some graph of a function. And I want to find the area between them. I want you to notice that the red is above the blue in this section. So if I want to find the curve between them, between x values of 0 and x value of 2, then I'm looking at this green area here. I can change whatever x values I'd like in this section. So maybe I find the area between these two curves from x value of 3 to x value of 7. Or maybe I find the area in between these two curves from x value of 9 to 10. Let me get to a 9 here. So this area here. What I am going to do in order to find any of those is I'm going to look at the section and I'm going to find the signed area for the red curve, and I'm going to find the signed area for the blue curve. So let me go ahead and do that. So we're going to go from 0 I should have had this, but that's okay. So if I want to find the green, what I start out with is I start out with the signed area for the red. And then I look at the signed area for this blue curve. The red is f of x. The blue curve is g of x, if you can't see that. So we're going to find the area in between by taking the signed area for f and then taking away this little piece that's underneath the blue, the g of x. So essentially what we're getting, and this is for whatever values we choose. So obviously I'm from 1.6 to 2 there, but if I wanted to start at 0 and go to 2, that's what I would do. So I'm taking the red minus the blue is giving us that green. Now you can do this even when our curve drops below the x-axis. So for instance, what would happen in this case where I'm going from, let's say, 10 to 13, is that the signed area for f of x would be up here, and the signed area for g of x, and I'm going to switch that to blue again, is a negative area. So basically what I would like to do is I take the red minus the negative area of blue. If I'm subtracting a negative, I'm adding this area. So I'm actually getting the red area plus a positive blue area when I subtract. So that's what we end up doing. Basically, it's just the signed area under one curve minus the signed area under another. Now, in this case, this red curve, the f of x, was on top, and the blue curve, the g of x, was on bottom. But if we go to another part of the graph, maybe over here, the blue is going to be on top, the g of x is going to be on top, and the f of x is going to be on bottom. So in this little section, we'd want to take the blue g of x minus the red f of x in this section if I'm looking for a positive area. The same thing over here. If I'm looking for an area between these two curves to get a positive number, I'd take the g of x minus the f of x, and then the signed area is what we get when we integrate. So I just take the top one minus the bottom one, and then I integrate from a to b, from my bounds. In this case, we can see that in that shaded region where I've shaded here, the line is above the parabola. So we'd have to take the line minus the parabola from 0 to 2 and then integrate that from 0 to 2. Excuse me. And that gives me the general formula for finding the area between two curves. If I want to find the area between f and g, all I have to do is integrate f minus g between x values of a and b. Now, this is going to give me the area whenever f is greater than or equal to g, so f is above g on that interval. Otherwise, it's a pretty straightforward operation. F minus g, definite integral from a to b, gives me the area. Again, as long as f is bigger than g. And if g was bigger than f, then we just switch these. So let's go ahead and do an example. We will find the area between y equals x plus 4 and y equals x squared minus 2 from x equals -1 to x equals 3. The first thing I typically do is graph my two curves. So one was y equals x plus 4, the other was y equals x squared minus 2. And we're going from -1 to 3. Now, between -1 and 3, that is x values of -1 and 3. We can see that y equals x plus 4, the line, is above y equals x squared minus 2, that is the parabola. So in my region, the line is on top. And so to find this area between them, we're going to take the line minus the parabola and integrate that from -1 to 3. And that'll give me the area between these two curves. So that's what I do. Area is equal to integration from -1 up to 3. And then we have to be a little bit careful about how we do this. The line is y equals x plus 4. So I got to put x plus 4 in parentheses. And then I'm going to subtract the parabola y equals x squared minus 2. So I subtract x squared minus 2. Be careful when you do that because the x squared minus 2 is in parentheses, and this minus sign needs to distribute. This is just a definite integral. So what I would do typically is I would just either utilize my calculator to do this, or maybe I would like distribute a negative and do some combining in my head and then use my calculator to integrate. You can also, if you'd rather, do all of the integration by hand as well in this case, because it's pretty easy to do. But you'll notice that if I do simplify, you'll get negative x squared. I'll put that out front. And then I have a single x. And then I'll have a plus 4 here and a minus a -2 there. So 4 minus -2 becomes a plus 6. So I just integrate that. And again, I probably myself would just plug this into the calculator, okay, without doing a simplification. But if you wanted to do it by hand, you would want to simplify first and then integrate. Nothing's really special here as far as how to plug it into the calculator. Again, you can use either option. I tend to use the first option because there's no need to do extra work. And what I ended up with is basically 18 2/3. So the area between those two curves, between -1 and 3, is 18 2/3. If you need help plugging things into your calculator to do a definite integral, then obviously you can do that. You can look at the video on definite integrals that we showed in the last section. So again, either way you want to plug that in, I tend to plug it in just using that. But if you want to simplify and plug it in, that's fine. If you want to simplify and then do it by hand, that's okay as well. Let's try another example. We're going to find the area between y equals 1/2 x to the third plus 2 and y equals x plus 1 on the closed interval between 0 and 2. Now, when we say on the closed interval between 0 and 2, all we're saying is from x value of 0 to x value of 2. So that means the same thing as the previous when I said x value from -1 to x value of 3. I could have also said on the closed interval from -1 to 3. This one is on the closed interval from 0 to 2. So that means from x value of 0 to x value of 2. If you want to try this on your own, push pause and try it. Otherwise, I will go ahead and do it. I have graphed these two curves on Desmos. You can also graph them on your TI-84 calculator. That's what I would do if I didn't have access to Desmos. I would just use the TI-84 calculator and graph them that way. You'll notice that between x values of 0 and 2, the cubic equation is above the linear equation. So this cubic, which is 1/2 x to the third plus 2, is above y equals x plus 1. So that's what we're looking at. And just as a visual, I haven't. We're looking at the area of that section between x value of 0 and an x value of 2. Again, usually I just take the TI-84, but on my computer, it's easier to display Desmos. So the cubic is above, so we write 1/2 x to the third plus 2 minus the quantity x plus 1, and we're going to be integrating that from 0 up to 2. And at this stage, I just reach for my calculator and type in that definite integral. So I'm going to go ahead and do that. I know you can't see that, but there is the definite integral video that shows you how to do this, not this particular one, but how to do definite integrals on your calculator. If you want to simplify by distributing the minus sign, you can. If you want to combine like terms, you can. But I'm just plugging it in here, making sure to keep parentheses around this x plus 1, this second function. It turns out when you integrate that area, you get 2. So your final answer is just 2. This should be pretty surprising that we get a whole number. That was a kind of a weird shaped area, and we ended up getting that weird shaped area has area of exactly 2. Again, that's the area in green here. So even though we had some weird curves, the x to the third curve, and we had the x plus 1 line, this area between them is the nice whole number of 2. 2 square units, whatever units we'd be dealing with. If these measurements were in feet, it'd be 2 square feet. If these measurements were in centimeters, it'd be 2 square centimeters. So whatever our measurements are in, it's 2 square units. So far, the x bounds that I've been using have been given to us. But oftentimes curves intersect. And when those curves intersect, they create closed and bounded regions. So what I mean by closed and bounded means a finite region of a finite area that's entirely enclosed by the curve or by the curves. So there's multiple curves here. So we would like to find the area of a closed and bounded region. Again, closed means it's completely contained, where its boundary region is formed by the curves we're talking about, and bounded means it's finite. So closed and bounded regions are often things that we want to find the area of. When I do that, to find the x-bounds, a lot of times I'm going to need to find the points where the two curves intersect. And it may be more than two curves, as we'll see later. So we'll look at some tools to find where points intersect. You can use your calculator to find where points intersect. You can use algebra to find where where curves intersect, and so on and so forth. So let's try to find the area of the region bounded by f of x equals negative x squared plus 4x plus 1, and g of x, which is x plus 1. The first thing I'm going to do is I'm going to graph these two functions and look to see if I can find the closed bounded region where the boundary is created by these two functions. I graphed on Desmos, but there's some tools on the TI-84 that would actually be beneficial to use if you were graphing with the TI-84. So you can graph on Desmos, graph on TI-84. For the purposes of this, both work just fine. In this case, you'll see that there's a lot of different bounded regions. There's this region in here where the line is above the parabola. So in other words, where this purple region here, all right, the line is above the parabola, but it's not bounded. It goes on forever down here, okay? These two curves also make this region, but again, it's not bounded either. It goes on over there. The two curves also make this region. That obviously is unbounded. Any of this region over here is unbounded. The only closed and bounded region that these two curves make is the one here. Now, visually, we can kind of see what's going on. Visually, we're looking at a region from x equals 0 to x equals 3. And on that region, the parabola is above the line. So in this section, for the closed bounded region, the parabola is above the line. Now, if I'm using my TI-84 calculator and I can't see where this point of intersection is, I can't see that it's 3, 4, you can actually use your calculator to find points of intersection after you graph, you use the calculate menu. I'm not going to show that on this video, but I may show that on supplemental video. So you can find points of intersection if you're having a hard time using the TI-84. Desmos, a lot of times you can just hover over the point and click on it. Although sometimes if you get ugly numbers, they might not be recognizable. These are really recognizable because they're all whole numbers. So we're going to be integrating from 0, again, x value of 0, to x value of 3, and my f is above my g. So the f is above the g. We take the expression for f, which is negative x squared plus 4x plus 1, in parentheses, and subtract the expression for g, which is x plus 1. Just make sure that that is also in parentheses. And we're going to be integrating, like we said, we found that the bounds go from 0 to 3. Just as a side note, there are other ways to find these bounds, the 0 to 3 as well. One other way to find those bounds, if I wanted to find the bounds algebraically, is just to set the expressions equal and solve. So I'd set negative x squared plus 4x plus 1 equal to the expression x plus 1, and then I'd solve. I would probably just add x squared to both sides and then subtract 4x from both sides and then subtract 1 from both sides to get 0 on the left. And then on the right, I'd get x squared. When I subtract 4x, that would give me a minus 3x on the right. And when I subtract 1 from both sides, I get 0. And this gives me an equation I can solve for x. I'll do that through factoring. So either x is 0 or x minus 3 is 0. And then that gives me my two places of intersection. One is x equals 0, and obviously the other is x equals 3. So if you can't utilize tools on your calculator to find the intersection, or you can't utilize Desmos, you can always do it algebraically. But primarily, I'll use the calculator tools. Now, that's all said and done. We have our bounds now. So now we want to integrate, again, the expression for f minus the expression for g. And when I type that into my calculator, I got a 4.5 or 4.5. So the area between those two curves from 0 to 3 is 4.5 square units. Let's try another example. Let's find the area of the region bounded by f of x equals square root of x plus 3 and g of x equals 0.5x plus 3. So we're going to have to find a closed bounded region that these two equations form. Usually I would just graph that on my calculator. Since I don't have the calculator displayed right now, I will graph it on Desmos. When I graphed the two curves, the root x plus 3 was this curve with a little bit of, not straight. And the x plus 0.5x plus 3 was this line. All right. So 0.5x plus 3 was this line. Root x plus 3 was this a little bit curved. And you can see that there's a few unbounded regions around this, but the only one that is closed and bounded is this region in here. Let me shade that. Now, it goes from 0.03 as one intersection to the 0.45 as the other intersection. Like I said, if you're using the TI-84 calculator, you can use that to find the points of intersection. You could have also algebraically found where these two curves intersect by setting the expressions equal to each other. But for here, all I really need is to say x values go from 0 to 4, and in that region, the square root of x plus 3 is above 0.5x plus 3. I won't find points of intersection this time. I'll just say what we have. So we're integrating from 0 to 4. I saw that on the graph. And in this case, the square root of x plus 3 was on top, and the 0.5x plus 3 was on bottom. I do want to mention that in both examples that I've just done, the F was above the G, but that is not always the case. Sometimes the G could be above the F, and then you'd be subtracting in the other direction. If you wanted to do this by hand, you could. I typically don't want to do it by hand. I want to do this as efficiently as possible. So square root of x plus 3, I put that in parentheses, and I subtract in parentheses 0.5x plus 3, and I integrate that from 0 to 4. When I do that integration, my calculator gives me out 1 point, then lots of 3's, and then a 5, 4, 4. So my calculator, whoops, gives me out this number, okay? And because we have a square root and we're dealing with 0, it turns out this is a good approximate number. Now, if you're asked for the answer rounded to 2 decimal places, the answer rounded to 2 decimal places is 1.33. However, if you would have done this by hand, what you would have gotten by hand is 1 1/3. Or, if you'd rather, you could have written that as 4/3. Again, the decimal approximation your calculator is doing doesn't give you exactly 4/3, but it does round correctly if we're rounding to 2 decimal places. But this is one of those cases where definite integrals can give me very close to the real answer, but the tools my calculator is using gives me a very close answer. So that's the area in this case. In most of my classes, I asked to round to 2 decimal places. And so you get the same either way. But that is the area between those two functions from 0 to 4. Let's look at another example. Now, this example, we have 3 curves that are going to create this region. One of them is g of x is equal to 4 over 2 minus x. The other curve is the line y equals 4. And the other is the curve x equals 0. So the line y equals 4 obviously is a horizontal line. X equals 0 is a vertical line, specifically the y-axis. And then we have this 4 over 2 minus x. I'm going to draw all 3 of these and find the closed bounded region that is created with all 3 of these on the perimeter. When I graph these three curves, again, x equals 0 is the y-axis. Y equals 4 is this horizontal line. And g of x is equal to 4 over 2 minus x is this rational function that is split essentially into two parts. So this curve here is the curve g of x is equal to 4 over 2 minus x. 4 over 2 minus x. Again, you'll look at these three sections give a lot of, they split the Cartesian coordinate plane into a lot of different pieces. There's a piece over here and a piece over here. The only one that's actually finite and bounded and using all of my curves as one edge is this section in here. Notice that this section is not quite a triangle. It's kind of triangular shaped, but it has a curved side. But the x values on this go from 0 to 1. In this region, the curve on top is the y equals 4 curve, and the curve underneath is that g of x is equal to 4 over 2 minus x curve. So that's what we need. And again, if we shade it, it's this shaded region here. So we're trying to find the area of this shaded region. And what I'm arguing is that my x values are going to be going from 0 to 1. The curve on top is going to be y equals 4. The curve on bottom is going to be g of x is equal to 4 over 2 minus x. Again, this one was pretty easy to see algebraically. So, but you could have also found the points of intersections by setting these two equal. Set 4 over 2 minus x equal to 4, and then you could solve and get 0 and 1 as your two, or not, 4 over 2 minus x, you'd get that 1 point of intersection. And then you could set x equals 0, obviously, is the left-hand part of that region. So 0 to 1, you'd have gotten 1 point of intersection. If I set y equals 4 equal to 4 over 2 minus x. So first expression is y equals 4, so we just write down 4 minus second expression is 4 over 2 minus x. So we write down 4 over 2 minus x, and then we can integrate. Now on this one, when we integrate, it's going to be, we have to type it in carefully, obviously. Sometimes people like to distribute this negative, but the key thing is when you do 4 divided by 2 minus x, make sure you put 2 minus x in parentheses if you're typing this into your calculator. It comes out as about 1.23 as the area. My calculator actually gave me 1.227411278, which if I ask my calculator what fraction is that, it doesn't know what fraction that is because it's not a nice one, okay? In fact, if you were to try to find the actual antiderivative here, you'd have to use natural logs, and That's what happens. So you'd end up with a natural log of something. Okay. So that's where that ugly decimal is coming from. It's coming from a natural log of some value. But for the most part, if we're fine with approximations, we're good to go. And we can just type it into our calculator if I'm just fine with approximations, which generally speaking in my classes, we're going to be fine with approximations. Okay. If you did need an exact value, then you'd have to go back and find the antiderivative of 4, find the antiderivative of negative 4 over 2 minus x by hand, which is just a natural log calculation, and then plug in 0, plug in 1. So there we go. Let's do another example. In example 6, we want to find the area of the region that is bounded by these three curves. Y equals 2x minus 5, y equals 0, and y equals x. You can try this on your own if you'd like by pushing pause on the video, but I will show how it's done in just a few seconds. I've graphed all three of these curves. Well, these all three are lines, but I've graphed all three of these on Desmos. It's pretty easy to see the closed bounded region that we're talking about because all of these other regions are unbounded. They're infinitely big. And by the way, that's why we don't calculate their area because their area is going to be infinite. The region that I'm looking at is right here. So basically, if I was to shade it, it's this region. I'm just trying to shade poorly, but it's this region in here. Okay. Now, here's the weird thing about this region. When you go from x equals 0 to x equals 2.5, this first piece, the top curve is y equals x, and the bottom curve is y equals 0. However, on the other side of 2.5, of x equals 2.5, the top part of this region is this y equals x, and the bottom part of the region is y equals 2x minus 5. So that means that I'm going to have to split this region up into two areas if I want to figure out the total area of the region. The first area is going to go from 0 to 2.5. Y equals x is on top. Y equals 0 is on bottom. And the next region goes from x equals 2.5 to x equals 5, because that's that point of intersection, with y equals x on top and y equals 2x minus 5 on bottom. So I split this up at x value of 2.5, and part of my integration is going to go from 0 to 2.5, and then the second part of my integration is going to go from 2.5 up to 5. And I have to do that because the curve which is on top and bottom changes at x value of 2.5. I can also find, all of those points of intersection algebraically if I'd like. I'm not going to do that. But my total area now we can see is going to be a set of two areas. One where I go from x value of 0 to x value of 2.5. In that section, y equals x is on top. So x is my expression there. And y equals 0 is on bottom. So I plug in the expression of 0 there. In my other region, the other region goes from x value of 2.5 to 5. And on the top of that region is still y equals x. But on the bottom part of that region is bounded by 2x minus 5. Now, this is how you do it through calculus. You can obviously, because these were nice triangles, you could probably figure out the actual area through triangular calculations as well. I'm not going to go and do that. I'm just going to do the integration. So in my first integration, when I integrate from 0 to 2.5 of x minus 0, this one's easy to simplify if you want, just leave off the minus 0. I get 3.125. And then in my second integration, I'm going to integrate from 2.5 up to 5. We're going to take x minus the quantity 2x minus 5. If you want to distribute and combine, that would give you a negative x plus 5. And it turns out I get 3.125 for that section as well. And so that means the total area is 6.25 when I add those together. So the total area of the region bounded by these three curves is 6.25. That's going to happen sometimes, especially when the top and bottom curve aren't always on the same top and bottom curve. So, like I said, like in this case. By the way, um, again, there's my x equals 2.5. That's the line that's splitting this into two regions. And I could have, if I wanted to, have done um, all of the calculations by hand and found that the area of this triangle, the triangle from 0 to 2.5 with height of 2.5, so I would have taken 2.5 times another 2.5 and then divided by 2. That's the area. That gives you the 3.125 here. And then the area of this triangle, well, you can think of this as the base. The base goes from 0 to 2.5, and then the height would go from 2.5 to 5. So once again, 2.5 times 2.5 divided by 2 is the area of that triangle, which again is 3.125. So if you wanted to, you could do this geometrically, is all I'm saying. Now, if you had other curves, you couldn't do it geometrically. So if this green curve were some cubic or some quadratic equation, then obviously you'd have to use the calculus tools that we have. So that's why I tend not to use geometry, because not every time do I have straight lines. But there you go. That's the area. We said 6.25 is the area of this bounded triangular region. Let's do another example. In example 7, we want to find the area of the region bounded by y equals 1/5 x squared, y equals 0, and y equals 10 minus x. I will go ahead and graph those in a couple of seconds. If you want to try it on your own, push pause, and I'll give you a couple of seconds to do that if you want to try it on your own. All right, I've graphed these 3 curves. Now, don't get confused. The x-axis is the line y equals 0, so it's down here. Sometimes people misread this and they say, oh, y equals 0, and they put the y-axis, and then it gives them this closed bounded region or this closed bounded region. That's not what we're looking at. In fact, if you notice, there's a couple of closed bounded regions in this graph. One of them is here, even if I don't use the y-axis. One of the closed bounded regions is here. That goes from the y equals 10 minus x down to the parabola. But the only closed and bounded region where all 3 of our curves represent the perimeter of the closed and bounded region is this section here, this almost triangular shaped section. So again, don't get confused with that. If it says the closed bounded region bounded by all 3 curves, we're looking for a region whose perimeter hits all 3 curves. This region is closed and bounded by y equals 10 minus x and y equals 1/5 x squared. But y equals 0 is really not on the perimeter of that region. So we're talking about this region, this closed bounded region here. Now it's pretty easy to either calculate or use your calculator to find the points of intersection. You can algebraically find points of intersection of all 3 of these pretty quickly as well. But our points of intersection here are the origin, the point 5, 5, and the point 10, 0. You'll notice that between values of 0 and 5, this region on top is bounded by y equals 1/5 x squared, and on bottom is bounded by y equals 0. After you get to 5 and beyond, then the top of this region is bounded by y equals 10 minus x, and the bottom of that region is once again y equals 0. So what we're going to need to do is break this region into 2 pieces, find the area from 0 to 5, and then find the area from 5 to 10. So that's what we're going to do. And obviously from 0 to 5, y equals 1/5 x squared is on top, y equals 0 is on bottom. From 5 to 10, y equals 10 minus x is on top, y is equal to 0 is on bottom. So let's set this up. So the area is going to be a sum of 2 different integrations, one going from 0 to 5 and the other going from 5 to 10. The one that goes from 0 to 5 has 1/5 times x squared on top. and y equals 0 on bottom. The one where we go from 5 to 10 is going to have 10 minus x on top, and y equals 0, or just 0 on bottom. So we always write the expressions for the functions in there. Then I turn to my calculator, probably. You can also do this by hand. None of these are real tough to do. If you want to do it by hand, that's perfectly fine. If you want to do it via your calculator, that's perfectly fine as well. The first definite integral turns into 8 1/3. When you integrate the second definite integral, that turns into 12 1/2. So when that's all said and done, you get 20 5/6 as your total area. Eight plus 12 is 20, 1/3 plus 1/2 is 5/6. And obviously, a lot of times people will round that number to 2 decimal places. If you round that number to 2 decimal places, you get 20.83. Whichever answer is asked for, you can do that. Again, you can do that by hand as well. It's just faster to do with the TI-84 using the definite integral feature of that TI-84. So this is how we find the area of closed and bounded regions. We have to look through the region, look at the region, figure out which closed bounded region we're talking about. The one that we're talking about is always going to have all of these curves as a piece of the perimeter. And then also going to have finite area. Once I do that, then I either do one integration or maybe multiple integrations to find the area. And to do these integrations, it's just a definite integral calculation. We kind of saw this in the last example, but not precisely. In our last example, we had multiple bounded regions, but only one of those regions shared all 3 curves as the perimeter. But there are also times when we create a curve, and even with just 2 curves, we have multiple bounded regions to pick from. So if there's only one closed curve that uses all sides, all the sides intersecting as the perimeter, then we'll use that region. But there are certain times which it's ambiguous which region we should use. If there are multiple options, then we need a little bit more clarification. Let me give you a bad example. If I asked someone to find the area of the region bounded by f of x is equal to the quantity x minus 1 to the 3rd power, and g of x is equal to x minus 1, it turns out that these 2 curves produce multiple closed bounded regions. So if I ask for the area, it would be a little bit ambiguous. Let's just graph these so that we can see what I'm talking about. So here are the graphs of those two curves. One is the straight line g of x is equal to x minus 1, and the other is the curve f of x is equal to quantity x minus 1 cubed. And you can see there's a lot of unbounded regions, but they've created actually two bounded regions. One underneath the x-axis where f is above g, and the other that's above the x-axis where g is above f. So if it said find the area of the closed bounded region, it's really ambiguous because they may be asking for this region here, they may be asking for this region here, or it is possible they may be asking for a combination of those two regions. Maybe they're asking for the area of this plus the area of that. Or maybe they're asking for this as a positive area and this is a negative area. So they might be counting this as a negative area because it's underneath the x-axis, or maybe because the f is above g, or maybe they want to count this as a negative area because the g is above f, and this is positive because f is above g. So maybe they want to count both areas as positive, maybe they want to count both areas as negative, maybe they want to count one as positive, one as negative. Maybe they only want to count one of the areas or the other. So that is a bad question because it's ambiguous which area to calculate and what they're asking us to do with it. Almost always when we talk about area, we're talking about positive area, but sometimes in application problems, one of these regions could be counted as a negative. That situation can happen whenever there are a bunch of intersections. When there are multiple intersections, then we can end up with some ambiguous questions. So we could, again, count one area as positive, one area as negative. We can count everything as positive. We could only count one of the areas. And so we need some clarification. Now, we can do some or create some clarification by just using another piece of information. Like, let's say we wanted to find the area of the region bounded by F and G in the first quadrant. If I add the fact that we're just looking at in the first quadrant, then I can see that one of my closed bounded regions was in the first quadrant. And therefore, I can just find the area of that region. The first quadrant is, again, the positive x's and positive y's, so above the x-axis to the right of the y-axis. And so the only region there in the first quadrant is this one. Therefore, we're going to be integrating from an x value of 1 to an x value of 2. And in this case, the g of x is on top of the f of x. So we're going to take g minus f, or the expression for g minus the expression for f, when I set up my definite integral, again, from 0, not from 0, from 1 to 2 in this case, because I'm just looking at this region here. Let's calculate this again. We're going from 1 to 2 on my bounds because that's where we intersected there. The top curve is the g of x curve. So I'm going to put in the expression for g of x first. So x minus 1 goes in first. And then I'm going to subtract the expression for f of x because that's the lower one. And that is x minus 1 to the third. I can actually write it like this. That won't throw anything off. So that is the calculation for my area. We can do this by hand if you wanted to expand the x minus 1 to the third out and then combine like terms. But I typically don't do it by hand. I just write it into the calculator using the definite integral feature of the calculator. And that becomes 0.25 or 1/4. So the area that I was looking at in that first quadrant was 0.25. And that's the setup. Now again, the area that I found was just this one of the closed bounded region in the first quadrant. So this shaded area is what is 0.25 or 1/4 of a square unit. I didn't include this one. You could actually imagine and you can see that this would also be 0.25 if I calculated the area down here. But I'm only asked to find the one in the first quadrant, so it is this green one, and that green area is 0.25. This shaded area here is 0.25. So that is it for this section. If I ever want to find area between two curves or area of a closed bounded region, I just can take the definite integral from a to b of the top one minus the bottom one. Sometimes if that changes, I have to add multiple integrals. I have to break my area up into pieces, but top minus bottom integrated from value a to value b. That is x value of a to x value of b. So that is the area calculations that we're going to do in a two-dimensional sense. We'll get into three-dimensional area like surface area in a later section.